So the final paper of this session is by bault and about time average regional model of the Hermean magnetic field. You want this one or the other?
Good afternoon. So I'm now turning to the internal magnetic field, mostly the core field, but we don't know yet exactly. So we have been deriving a model for the magnetic field using quasi-hemispheric method, and the rationale behind that is because, as you know now, the messenger probe has surveyed mostly the northern hemisphere in terms of magnetic field measurements important for the internal field modeling. The reason is that each time it crosses this magnetopause, we don't have access to the information from the internal field. And so we have been using the entire mission lifetime from March 2011 to April 2015. And this represents something like more than 5 million of measurements. So of course we have been selecting the data, only considering data in the northern hemisphere after the crossing of the magnetopause. We have been also using a quality index to select the measurements for quiet times, what we call quiet times. And then we have been using a regional method for that. So far, what do we know about the magnetic field of Mercury, the internal field? The work that was done recently all confirmed previous results. The internal magnetic field is rather weak, 300 nanotesla. It's nearly axis symmetric, and it has an apparent magnetic equator shifted northward. I'm really insisting about this apparent magnetic equator because we have no access really in the southern hemisphere. And the problem we have is that the offset dipole model currently implies a large ratio between the quadrupole and the dipole parameters in spherical harmonics, and this raises complications in terms of dynamo simulations. So we wanted to test if this was really robust or not. And so far we could not detect measurable secular variation, but secular variation usually we are thinking in terms of long-term variations of the magnetic field, so maybe there are shorter timescales of the magnetic field. And of course we don't have an ionosphere, so this complicates the separation of internal and external fields as reconnection may occur within the crust, and so far this was the main reason why spherical harmonics was not used. So I would like to stress that all these conclusions were drawn from measurements at altitude higher than 1,500 kilometers. And when you do that, any potential field or any field that is complex will tend to show a kind of dipolar structure. This is the nature of magnetic field. When you go very far away from the source, you tend to smooth out the small scales and have a large structure. So we wanted to know also if there were some small scale structures in the magnetic field of Mercury. So here are the numerical challenges. As I said, we have measurements only in the northern hemisphere. So spherical harmonics, which are global functions, cannot separate internal from external fields. You have a lot of covariance between the coefficients. This is illustrated here. If you just make a matrix of the spherical harmonics, you see that each time you add a new coefficient, it will covary with others. So it makes things very difficult when you want to study one coefficient or extract one coefficient from the others. So here I'm talking about this quadruple dipole ratio because both are correlated in fact. And also the data distribution, as you see, is as a function of the latitude here. It shows that at low latitudes you have high altitude measurements, and when you go to higher latitude you have smaller altitude measurements. So the configuration is not excellent. So we have been using a new method in this context. It's called the spherical cap harmonics. So the basic idea is to just consider a quasi-hemisphere here and to develop specific basis functions that are mathematically orthogonal. So when you do that, you get rid of this covariance of the parameters. And this makes things much easier because then you can go to very high expansion, local expansions, without covariance and numerical instabilities. And you can also derive power spectra to high resolution, and in terms of degrees and also orders of spherical harmonics. And here, this is a covariance matrix shown here. As you see, there are small covariances between parameters, but this was sketched on the real data distribution. And I showed that there is a kind of uneven distribution with altitude, for instance, and this is due to that. But in general, you can extract one coefficient and they are physically meaningful. So of course what we have to start with is synthetic analysis. So we developed a spherical harmonic model to spherical harmonic degree 10, synthesize the data on the real messenger data, add a noise, and then we derive the regional model and try to downward continue the model down to the core mental boundary. So there are two conclusions here. First one is that here this is the synthetic model in spherical harmonics. Here this is the regional model at the core mental boundary, and here are the residuals. First conclusion is that with this data distribution, we should be able to downward continue the field to the core mental boundary. So it's numerically very stable. And second conclusion, if there were small scales at Mercury, we should be able to detect them. And we will see that this is not the case, so which is a kind of interesting result. So, of course, you can also plot spectra here. As I told you, the spherical harmonic was developed, synthetic data were developed to spherical harmonic degree 10, and with the local functions, we went to spherical harmonic degree 18, and you see that there is a clear cutoff here. So there is little spectral aliasing, which was a good sign. And now the problem is that we always want to display everything in terms of spherical harmonics. And this is where complications arise. If you take only Northern Hemisphere data, you have orthogonality between the degree minus orders odd terms. So you should be able to extract these signatures. But because they are symmetric with respect to the magnetic equator. But once you have the magnetic equator shifted northward, then you need at least kind of even term. So in general, you add the quadruple term because this is the first one. And when you do that, you start having lots of covariances. And if you add the G40, for instance, you have even more covariances. So here we made a kind of analysis of that and tried to mitigate this problem, and we selected only the G20 coefficient and tried to extract all other L minus M odd terms. And if you just consider these kind of coefficients that were published by Anderson, for instance, at least with this approach, you see that you have lots of instabilities. If you consider this one, you are closer to the input model. So here, this is just a confirmation that numerically spherical harmonics are very unstable in this context. So the problem is that when you add a quadruple term, it always introduces covariances. So my question now is this quadruple to dipole ratio really robust? So we now show the result coming from the real analysis, and this is the azimuthal spectrum. So it's just a spectrum displayed as a function of the orders M, and at different altitudes, and it shows that when you go down to it's just a kind of assessment here, it's probably not physically really interesting, but it shows that when you go to the core mental boundary, the power spectrum goes flat. So it seems that the model is also able to predict the radius of the core mental boundary. At least it's in agreement with what is known about the mantle, for instance. If you look at the magnetic field itself, you also realize that it's able to separate to a first-ordered internal from external magnetic fields. And here it's displayed at the CMB, at the core mental boundary. And for the internal field, what is very striking is that there is no small scale at the CMB. So far, it's not a completely new result, of course, but so far this result was obtained using truncated spherical harmonics using this only dipole modeling. So it was a very coarse spatial resolution. This model goes down to 700 kilometers spatial resolution, and even with this, it doesn't show any small-scale model. So it raises questions for the dynamo process behind that, or could also be a confirmation that there is a stratified layer at the top of the core. And I will show another result here. If you now display the power spectrum, the one you are probably more familiar with, which is directly comparable to the spherical harmonics, you see that this power spectrum is mostly pink or reddish. And this is a confirmation somehow that there is a kind of layer filtering the smaller scale, because when you do add a stratified layer at the top of the core and put a dynamo process underneath, you should end up with this kind of power spectrum. So it's not fully conclusive, but this is a strong argument here. Another way to assess this regional model is to look at the location of the magnetic equator. Here it's just the magnetic equator shown from the data, so as shown as a probability density functions. And you see that the black is the model we derive. The red is when you consider only the internal field. And the yellow is the model of Anderson and coworkers. So they are all more or less agreeing with the data. So at least from that perspective, they are more or less equivalent. What is interesting also is that the internal and external field seems to cross around 1,000 or a bit more than 1,000 kilometers, which is about 1.43 radius of Mercury, and it seems consistent with the solar standoff distance. So it also seems consistent here. Now comes the transformation to spherical harmonics, and I selected again the coefficients I was mentioning earlier, only the quadruple term here. And this regional model was transferred or converted in terms of this truncated spherical harmonic model. We cannot go to high resolution in spherical harmonic. And when you do that, you end up with the M1 model showing that, in fact, the quadruple to dipole ratio is much lower than what was so far developed. And you have a stronger axial dipole and a slightly smaller quadrupole, and actually this octuple here is slightly larger. So the question now was, why is it so different from the model of Anderson? So we carried out another analysis, and we added more weight on the data near the magnetic equator, because in the model of Anderson and co-workers, they derived this model by just trying to find out where the magnetic equator was. And they assumed that this was really the parameter that had to be fitted by their model. And if you do that, so in the inverse problem, you just add 20 times more weight on the magnetic equator data than elsewhere, you end up with the M3 model here, showing now that you have an increase in the quadruple term and a decrease of the axial dipole term, and also a decrease of the octuple term, and you end up with similar values as the one of Anderson et al. So it seems to us that these values, which are important for dynamo understanding, are probably constrained by the method that was applied to derive this offset dipole model. I'm not saying that this one is better, but in fact, this has no constraint in it. Of course, this is a quasi-static model, and what is interesting here, I'm not going into the details because it's completely outside the current topic, but if you look at the residuals, you see that there are lots of signal remaining to be modeled in the messenger data, in particular with local time here, and also with year. I think there are periodicities and showing that the magnetic field is varying every 88 days, every 176 days, and this is quite regular. So we are trying to investigate also this aspect. So as a summary, I would say that we have derived the regional magnetic field model from messenger data to 700 kilometer spatial resolution. So we have no truncation, artificial truncation in this model. We estimate that most of the conclusions raised so far about the mean strength dipole moments are confirmed by this regional model. It allows also to perform spatial spectral analysis and to separate internal and external field. And when you do that, you see some structures in the power spectra that are consistent with the stratified layer at the top of the core, in particular this pink or reddish power spectrum. And also the fact that we don't see any small scale features at the core mantle boundary. So we argue that if you want to really investigate dynamo theory, maybe you should not get impressed by this quadruple dipole ratio, because it seems that this is a kind of constraint that is implicitly brought by the method used by Anderson and co-workers. Thank you.